The Great Wall of China stretches over 13,000 miles across some of Earth's most extreme terrain. But how did ancient engineers accomplish this monumental task without modern machinery? The reality is far more complex than the myths suggest. Contrary to popular belief, the Great Wall wasn't built in one continuous effort. Construction spanned over 2,000 years, beginning in the 7th century BCE and continuing through multiple dynasties. Each era brought new engineering challenges and solutions. The first major construction phase began under China's first emperor, Qin Shi Huang, around 220 BCE. He connected existing fortifications into a unified defensive system, mobilizing hundreds of thousands of laborers in a massive logistical operation. Labor organization was the first engineering challenge. The wall required millions of workers, soldiers, peasants, convicts, and prisoners of war. They worked in rotating shifts, with specialized teams for different construction tasks. Materials varied dramatically by region. In the western deserts, engineers used local sand and gravel mixed with tamarisk branches. In the mountains, they quarried local stone. Each material choice was a calculated engineering decision. The most revolutionary technique was tamped earth construction. Workers placed soil between wooden frames, then pounded it layer by layer with heavy rammers. This created walls so dense they could withstand centuries of weathering. In rocky regions, stone masonry reached extraordinary sophistication. Workers cut stones to interlock perfectly without mortar in some sections. The precision suggests specialized stonemason teams with advanced measuring tools. Transportation logistics was staggering. In remote areas, materials had to be carried by hand or with simple carts. Some sections required building temporary roads just to transport construction materials. The Ming Dynasty perfected brick production on an industrial scale. They established kilns along the wall's route, producing standardized bricks that could be transported efficiently. This revolutionized construction speed and quality. Ming engineers developed advanced mortar using lime and sticky rice. Yes, rice. The amylopectin in rice created a mortar stronger than many modern cement mixtures. This biological engineering was centuries ahead of its time. Terrain adaptation was perhaps the greatest engineering triumph. The wall climbs steep mountains, crosses rivers, and traverses deserts. Engineers developed different foundation techniques for each environment. In mountainous regions, workers carved foundations directly into bedrock. This prevented erosion and provided stability during earthquakes. Some sections were built on slopes as steep as 70 degrees. Desert sections presented unique challenges. Engineers built reed and tamarisk mats beneath the walls to prevent sinking into sand. They also designed special drainage systems to handle flash floods. River crossings required sophisticated hydraulic engineering. Some sections had water gates that could be opened for boats. Others used arched bridges integrated into the wall structure itself. Watchtowers weren't just observation posts, they were engineering marvels. Spaced at arrow-shot intervals, they provided overlapping fields of fire. Their construction required precise alignment across vast distances. Signal systems allowed rapid communication across thousands of miles. Beacon fires, smoke signals, and flag systems could relay messages from one end of the wall to another in just hours. Military infrastructure extended far beyond the wall itself. Garrison towns, armories, and training grounds were built behind the wall. This created a complete defensive ecosystem supporting hundreds of thousands of troops. The human cost was staggering. Historical records suggest up to 1 million workers may have died during construction. Many were buried within the wall itself, though this was more myth than common practice. Quality control was remarkably sophisticated. Bricks were stamped with production information, which kiln made them, which team laid them. This accountability system ensured construction standards were maintained. Maintenance was a continuous engineering challenge. Special repair teams constantly worked along the wall. They developed techniques for repairing different materials under various weather conditions. The wall's width varied strategically. Main thoroughfares were wide enough for 5 horses abreast, allowing rapid troop movement. Narrower sections forced attackers into choke points. Parapets and battlements were carefully engineered. Crenellations provided cover for defenders while allowing arrow fire. Drainage spouts prevented water damage while doubling as defensive openings. Some sections featured hidden defensive features. Trapdoors, hidden arrow slits, and collapsing walkways were engineered to surprise attackers. These psychological warfare elements were as important as physical barriers. The wall influenced regional ecosystems. Its construction affected water flow, animal migration, and even local climate in some areas. Ancient engineers had to consider these environmental impacts. Supply logistics were monumental. Food, water, and equipment had to reach remote construction sites. Engineers developed relay station systems and storage solutions that functioned like ancient supply chains. Some of the most impressive engineering appears in seemingly impossible locations. Sections built on knife-edge ridges required workers to be lowered on ropes. The risk was immense, but the strategic advantage was worth it. The wall incorporated natural defenses brilliantly. Engineers used cliffs as living walls where construction wasn't needed. They integrated the wall with natural rock formations to create seamless barriers. Different dynasties left their engineering signatures. Chin sections show rough practicality. Han walls demonstrate refinement. Ming constructions reveal peak engineering sophistication. Each era built upon previous knowledge. The wall's effectiveness wasn't just physical, it was psychological. Its sheer scale demoralized potential invaders. The engineering achievement itself became a weapon of deterrence. Modern engineering analysis reveals astonishing precision. Some sections show alignment accuracy within centimeters over miles. This suggests sophisticated surveying techniques lost to history. The wall's legacy extends beyond defense. It facilitated trade along the Silk Road, provided border control, and became a symbol of Chinese engineering prowess. Its functions evolved with China's needs. Preservation today requires understanding original engineering. Modern restorers study ancient techniques to maintain structural integrity. The wall teaches ongoing lessons in sustainable construction. The Great Wall represents humanity's most ambitious pre-industrial construction project. It showcases problem-solving across generations, adapting to every challenge terrain and technology presented. Engineering reality transcends the myths. This wasn't just a wall, it was an integrated defensive system, a transportation corridor, and a demonstration of organizational genius. The true marvel is in the details. The workers' legacy endures in every stone and brick. Their engineering solutions, from rice mortar to mountain foundations, continue to inspire modern builders. The wall stands as testament to human ingenuity against all odds.